In Chapter 6, we'll be discussing statistical inference. Boils down to two major topics in here: confidence intervals and hypothesis testing. In this chapter, we're going to be operating under a pretty common assumption that it's pretty much impossible to get true information about the entirety of a population. To go out and talk to every American would be very time consuming and very expensive. But we're going to want to know, for decision making processes, etc., what the population mean and population proportion are about certain things. Well, what's the difference? A mean is expressed in numerical value. Average income that you would have for a consumer in the United States. How many miles per day somebody has to drive to go to and from work. If you're a car manufacturer, figuring out how many cars you need to produce and how often you expect them to break down. Whereas a proportion covers categorical variables. And right now, as I'm recording this, it's an election year. It would be the portion of people that identify as Republican versus Democrat. It can't be measured in numbers, but it's still something that you can measure. It's impossible to analyze the entire population. So what we're going to do here is we are going to do a bunch of samples, a whole bunch of polling, and from the results of all of our polling, we're going to make some kind of statistical inference about what the population may be. The thing with this is once you have all the information, there's only going to be one mean or proportion for the entirety of a population, where samples of any given size might return a whole bunch of different results. They might be close, but they won't be exactly the same as the population. So we want a parameter, and a parameter, like mu, is the mean of the entire population. Well, we can't obtain that. What we're going to have to find is a statistic, a mean of a group of people that we are sampling, or our X bar. And we're going to use this X bar as an estimator to make an estimate about the parameter. In layman's terms, we're going to find X bar for a whole bunch of different samples, and after we have enough information from those, we are going to assume that the average, if you will, of our samples is going to be equal to the population mean. So we're going to make an estimate of a particular value based upon our estimator. To do so, we're going to use a bunch of very similar formulas. Most of them make use of X bar, which is just the mean of our sample. And we're going to keep getting X bars back for every single sample that we take, because every sample is going to have a different mean. And from that, we can have a probability distribution. What is that? It means that for any one given sample that we take, what's the probability that the return on that sample, the mean of that sample, is going to meet a certain criteria. Drives more than 100 miles on average, makes more than $63,000 on average, whatever it is, we're going to be able to have a distribution of what every single sample looked like in our overarching huge quantity of information. So from that X bar, one thing that's incredibly important to this concept is that we want to have a high value of n. And n is the number of observations that we have in a sample. The bigger your samples are and the more samples you do, the greater n that you capture, the more it starts to look like a population. So the larger your sample size and the number of samples that you have, the more accurate you can assume that your data is. So we're going to repeat this process of sampling over and over and over again a large number of times, and from all those sample means we can develop a distribution, what any one given sample would look like on a normal curve. Whole bunch of information on this slide. Don't worry about too much. There's two very important things on here. First, we know what X bar is. We're going to have him. And we're going to expect in this case that our X bar is going to be equal to mu after we've got enough data up in this range. So the sum of all of our expected X bars that we would get from, when we find on average a sample has it, we're going to assume that that's the mu. The average of the sample means all of them is going to be equal to the average of the population. But we're going to have variance, and we know this. Not every sample is going to return a number that's exactly the same as the true population average in this case. So for variance, our formula is going to be the standard deviation of a population divided by our sample size. And with that, we're going to be able to set up a formula. But for that formula, we need a standard error. It's essentially our prediction on across all the samples that we do, what's the standard deviation of those samples going to be? And it is just the square root of the variance, because standard deviation is just the square root of the variance. So we're going to take the square root of this formula, and it turns into this formula. So for our formulas that we are going to use, our standard error, our expected standard deviation, if you will, is going to be equal to sigma, if we know it's the population's overall standard deviation, divided by the square root of our sample size, n. So let's put this into a more practical application. We are going to be a local pizza chain in Cambria, California, who have 16-inch large pizzas. And in a perfect world, every pizza that we made would be exactly 16 inches, because that's what we're advertising the size of our pizzas to be. Now, that being said, that probably doesn't happen. You're going to have some variance in the size of your pizzas. Some are going to be a little smaller, some are going to be a little bigger. So what we have here is we are assuming here that the population mean will be 16 inches, and that our standard deviation is 0.8 inches. So there is a little range where most of our returns are going to be either 0.8 inches below the 16 that we are expecting, or 0.8 inches above the 16 that we expect. And that distribution is going to be normally distributed. That's why the vast majority of them are going to fall within one standard deviation of the mean. So in this case, what value would we expect from any one pizza, or we need two pizzas, and what is the standard error of the sample mean if our sample size is just two pizzas? And we'll run it through one more time with the standard error this time in doubling the size of our sample up to 4 pizzas. So for both of these, our expectation through and through is going to be that a pizza is 16 inches. That's where our advertising, that's what we aim for. I think on average, we're going to get that right more than not. That's going to be our population mean size of a pizza, 16 inches. And we know that overall, across all of the pizzas that we have made in this thing, that our standard deviation of the population, sigma, is 0.8 inches. Well, what's the standard error for any one given sample that we would have in here? You find that by taking your sigma and dividing it by the square root of your sample size. So for 2 pizzas in a sample, we would come up with a standard error of 0.57 is our expectation. In this case, if we sample 2 pizzas, that there's going to be a deviation in size the overwhelming majority of the time, where the pizzas are going to be on average somewhere between a little over a half of an inch either below or above 16 inches. But if we double the size of our pizza, or the sample, excuse me, to double the size of the pizza, it'd be nice for the money, but double the size of the sample to 4, what happens with our standard error? Well, 0.8 divided by the square root of 4 comes out to 0.4, which means off of a sample of 4, we expect any sample of 4 that we take to only have a standard deviation for the average pizza in that sample of 0.4 inches, which is smaller right here. And that is the trend that you're always going to see. Your standard error is always going to be lower when you have a higher value of n. And the reason being is you might have one crazy 17.5-inch pizza in the sample, but it's highly unlikely that you're going to have 4 of them in a sample of 4 or 8 in a sample of an 8. So you might have one singular outlier that really messes up a small sample, but the bigger you make your sample size, the more you distribute that outlier's effect on your mean and your deviation. So over here we have some information about the pizzas where we're going to run another test right here. We're going to find the probability that a pizza randomly selected is going to be less than 15.5 inches, or if we take 2 and we average that out, what's the probability that the average of those 2 is going to be 15.5 inches. And we're going to use the same information we did before. Samples average is going to be x bar. Our expectation here, the mu, is that on average across all the pizzas that we make, the average is going to be 16 inches. And our standard error is going to be our accepted population standard deviation of 0.8 inches divided by the size of our sample. Well, in the first formula, we only got 1 pizza. So divided by 1 doesn't do anything for us. We'll just leave it as 0.8. If we take the spot in the information we're looking for, x in this case, in A, we are figuring out what's the probability that pizza is less than 15.5 inches. That's the point we're looking for. Compare that to our population mean, x minus mu, and divide it by our standard deviation. And the return that we get would be negative 0.63. And as you see here, that's expressed as a z. What is the z-score? It means that that return across the whole entire population will more likely than not be 0.63 standard deviations below the mean that we have over here. And the number associated with that is 0.2653. Well, how do you get to that? There's a whole bunch of calculations you could do. They are not fun to do. Back in the olden days, there's charts. Maybe you've seen some of them that have all the different possible z-values and what their p-value or probability is for that spot. But in a technology-based course like this one, it's a number that you can pull by inputting a formula. You can pull it from Excel. And in this case, we have 0.2653. 26.53%. That is the chance that if we pull any one given pizza, that it's going to be smaller than 15.5 inches. What about if our sample size is 2? What if we're saying we're going to pull 2 pizzas and the average size of those 2 pizzas will be 15.5 inches or less? Well, we'd run the same math right now, except on the denominator down here, we have to take our accepted population standard deviation and divide it by the size of the sample. And the answer to that formula is going to come out to be negative 0.88, which means for that to happen, for 2 pizzas to average out to be less than 15.5 inches, that average would have to be 0.88 standard deviations below the accepted population mean. And the chance of that happening is 0.1894, 18.94%. We have a little less than a 19% chance that if we make 2 pizzas like we normally do, not trying to fool the game here, just make pizzas as we do, there's a little less than a 19% chance that the average size of those 2 pizzas is going to be less than 15.5 inches following the same trend. It's more likely to have 1 mistake than it is to have 2 mistakes back to back. So what if you have a proportion? It's the same concept. You're going to follow the same exact steps through the whole thing. You're going to have to find what your z-score is, and it'll give you the probability of an event happening based upon your probability distribution from all the different samples that you would do. Only difference being is we got a few extra things, a few different things that are going to go into our calculations, and the first thing we need is p-bar. That's going to be the estimator that we use for this proportion, and it equals x divided by n. What is that? X is the number of people that meet the criteria out of n, the entire sample size. So if you went to 30 people and asked them how many preferred chocolate to vanilla, and 20 of them said, I like chocolate, well, out of those 30, better than vanilla, well, 20 over 30 would give you a p-hat of 0.6 repeating, which basically means that the expectation is that 66 some odd percent of your people in every sample that you take are going to prefer chocolate to vanilla. That's our estimator. As far as finding the standard error, the expected standard deviation based upon a proportion, this is your formula. It is the square root of the product of p and its complement, 1 minus p, over n, the sample size.